Hello, dear students, and my dear curious learners. How are you all today? I hope you're all doing really fine at your places. So, as we discussed last time on a topic called electrophilic aromatic substitution, we're going to discuss one more aspect of electrophilic aromatic substitution, which is nitration. Okay, students? So I have discussed in detail about aromatic systems. What is aromaticity? Please go to the previous lectures and do listen to the lecture provided on aromaticity, right? And also have a look at the previous lecture on electrophilic aromatic substitution, where I have in particularly talked about halogenation on purely aromatic system, which is benzene, right, students? So today we are going to be talking about nitration, right? Let us talk about nitration on the benzene ring. Nitration on benzene. This is yet another example of electrophilic aromatic substitution. So first step, is the generation of electrophiles. In many books or in many sources of study, you will see that generally it is described in two steps. First is the attack of electrophile on the aromatic system, and second is the regeneration of the catalyst used. However, I have told you a third, and which is the basic step, which is the generation of electrophile, right? So you can include it. It's not a wrong thing to do it. So, right. So let us talk first about the generation of electrophile. So you know that for nitration, you will be needing nitric acid, right? So what will be the catalyst over here? The catalyst that we take here, students, is this. Can you figure out what this is? This is sulfuric acid, students. H2SO4, which is your sulfuric acid, right? Now sulfuric acid, as you know, you can just represent it like this. Let us now write the structure of nitric acid. Now I generally have the habit of putting in all the lone pairs when I am drawing the structure of a particular acid or any particular compound per se. So you can also do it, and it makes life much more easier, right? So let's just see when this is breaking off. So oxygen is more electronegative. This comes out with all the lone pairs, all the shared electrons, right? And this is going to attack here since H2SO4 is an acid. So, and a proton is going to come out of it, right? So, water is going to be abstracted out. Plus C, the nitrogen is going to have a positive charge on it, because this bond is going to be both the electrons of the bond are going to be taken away by the oxygen atom, and it's going to attack over here, right? So NO2 plus. So this is our electrophile, students. This is the nitronium ion. This is going to attack on the benzene ring. Plus it is going to form the HSO4 minus ion, right? Because H plus has been abstracted from it, and the minus charge remains on the oxygen, right, students? So this is the first step, which is the generation of electrophile, which we have seen now. Now let us talk about the attack of the electrophile on the benzene ring. Now I would advise you, students, to keep on noting the reaction mechanism as we are going along, because if you write each and every single step of the mechanism, it becomes very easy for you to revise the time when you are actually reading it again for your exam, for your revision, right? So let us now come to the attack of the electrophile, which is the nitronium ion, which can be represented like this on the benzene ring system. So let us form this. Okay. So you know that the attack of the electrophile or the formation of the sigma complex or the Wheelan intermediate is the rate determining step here. It is the slow step, and it determines the rate of the reaction, as I have discussed in a lot of detail in halogenation also, students. So let's go to this. Okay. Now what is the electrophile here? Let us just put that. Okay. NO2. Okay. So this has taken up the pi electrons. So there's a positive charge here. Alright, students. So this can be shown, let us just draw the resonating structures of this, and you will see how it is being stabilized, as I showed you earlier for the chlorination and bromination also. So this is one structure. I'd like to just draw the structure over here. Alright. Okay. So since we are drawing resonating structures, they must be enclosed in square brackets. Okay. Alright, let's draw this. Okay, students. See this? Okay. So 3 resonating structures here. So we can draw a resonating hybrid or a resonance hybrid over here, students. Let us see. See? Alright. So this we have a resonating structure. So this is the second step where we are showing the attack of the electrophile onto the aromatic system. See, this is just like the addition of an electrophile onto the unsaturated systems which are not cyclic. Remember the electrophilic addition on alkenes. So this step is very much similar, but however in the second step it's not going to fully add, it's going to substitute the hydrogen which is attached. So that is what is going to be the main difference between aromatic systems and the unsaturated system, students, right? So let's look at that. So have you taken down this step? So I'm moving down to the next step. Start rubbing from here. Alright. So I'll redraw this intermediate here. Right? Let's do it. So we have this intermediate, students, right? Like we have this, right? So you can show the loss of H plus and it's going to form this, right? This, okay. So this H plus which comes, and you remember HSO4 minus being generated in the first step, it was the catalyst, and H2SO4 is regenerated. Apart from being the catalyst, we use H2SO4 specifically in nitration because it is also a dehydrating agent. Dehydration means loss of water, right? So it helps in taking off the molecule of water which was generated in the very first step when we were generating the electrophile, that is the nitronium ion, right? There it takes up that water molecule, it absorbs that water molecule. So apart from being the catalyst, it is also the dehydrating agent here, students. So you need to look here that this is the mechanism of the nitration, and we use very concentrated fuming nitric acid and very concentrated sulfuric acid, and the sulfuric acid must not have any water molecules absorbed onto it before, right? So it must be a dry sulfuric acid. So some people do use the zeolites to dry up the sulfuric acid which is already there, right? So no more absorbed water molecules, of course, from what is already there in the H2SO4, right? So it must be both the acids must be very concentrated for this process to occur in the laboratory, and it's a very successful reaction with high yield.